Okay, so today I will discuss bolometric experiments for double beta decay, and this is a picture of that illustrates the results obtained with the more sensitive experiments that are operating or have been operated in the recent past in this field. So the first 4 experiments are use the bolometric techniques. These other 3 experiments use germanium diodes, and these 2 experiments are using xenon in a TPC. So you see that the different results. I remind you that this bar is the translation of the half-life limit that you set once you look at the result into a translation into this parameter that is the Majorana mass of neutrino, and the width of the bar is due to nuclear matrix element spread. So it's not exactly an uncertainty, is spread according to the different nuclear models. So you see that more or less we are what we say is that this experiment, we call them, and we classify experiment with the word generation. So the present generation experiment is investigating the parameter space that corresponds to the inverted hierarchy. And the goal of the next generation experiment is to be able to fully explore this energy region, this mass region, and therefore, if possible, to achieve more or less a result that lays here. And among this new generation experiment is Cupid, that is an upgrade of the core experiment. So we started developing the large mass bolometer and in the 90s and in Milano, and we were the first group working on big size detectors. At the beginning, we started with small size detectors. The choice of tellurium was done on the basis of the high Cuvier and especially on the high isotopic abundance. And that means we were able to start with a reduced budget because enrichment is extremely expensive. And then we started with tellurium, that is a semiconductor, but it's extremely, I mean, tellurium crystal has a structure that is called the spaghetti structure. So they have a very strong bonding in one direction, but not in the others. And that means that once you cool it down, when you warm the cryostat, you discover that you have pieces of crystal and no more crystal. So we were able to operate only once a bolometer, but with very bad results. Then we discovered that this company in China that was able to grow tellurium dioxide crystal. This is a dielectric, is a transparent crystal. And we started using this crystal that work very well at low temperature. At the beginning, we purchased a crystal of 100 grams, and we tested it in Milano. We had a cryostat in Milano, but we were not able to cool it down to base temperature. The cryostat that we are using generally are they have a base temperature of 5 millikelvin when nothing is inside. You do not have electronics, wiring, and so on. And when you deploy a detector, generally you are able to achieve temperature that are a few millikelvin higher than 5. But we were not able to cool it down. Can you guess why? I mean, I'm asking because you do not need important information and you can. Yeah, we had to cut it to small piece and then we were able to cool it down. No, when you cool it down, I mean, you close your crust, you put your detector in the cryostat, then you have thermal connections that on all the edges of the crystals, and so it was not a problem of thermalization. Exactly. The cosmic rays were warming up the crystal. Cosmic rays and environmental radioactivity. We were using a cryostat that did not have any shield. Was warming up the crystal. At the end, it's a power dissipation on the crystal, and this power dissipation was too high. Therefore, now we are able to test. We know that we are able to test the crystals at sea level only when they have a small size. 1, 2, 4 cubic centimeters, not more. 10, 20 grams. Yeah. There's we had to go underground to solve the problem. If this is what happens is that you know, assume this is the timeline and you have the voltage or the signal output of your crystal. In general, you have, I've shown you yesterday, a pulse like this. If you have more pulses, you will have something that is pile up, okay? We call this pile up, 2 pulses that are close. They are have a time distance that is smaller than the decay time of the pulse. But assume that I have a huge amount of these pulses. What happens is that I see something like this. And when they are very, very close together, I have, so what you can do is you can consider the flux of cosmic rays, millimolds, evaluate what is the rate of cosmic rays in your volume, the amount of energy that is released, and from that you evaluate the power that is dissipated, and you have to know which is the power that you remember yesterday I told you a cryostat is a refrigerator is characterized by the cooling power. Therefore, the amount of power that you can inject in the lower temperature part, I mean, in the mixing chamber or where you deploy the detector, the maximum power that you can dissipate there without increasing the temperature of your cryostat. And so we discovered that the problem was there, and there is no solution for that problem. Because shielding, when you add the shields, you get a worse condition because you have the cosmic rays produce showers, and so you have much more events in your detector. So you have to go underground. It's not needed to go really deep underground as in Gran Sasso. But for us, the solution was to go underground in Gran Sasso, and we installed the cryostat in the underground hall A that is still operating. and it was installed at the beginning of the 90s. And then we added a cryostat, a test cryostat with smaller in Hall C, and now we have the big core cryostat again in Hall A. So let me just summarize you how tellurium detectors are constructed and how they are operated. As I told you, we have a crystal, tellurium dioxide crystal. We glue on the crystal a thermistor. This thermistor has this behavior. Its resistance changes with the temperature. And then I put some bias on this thermistor. Indeed, what I do is to use a biasing circuit that inject a constant current into the thermistor. And I mean, the way I keep this current constant is that I use two load resistors that have a resistance that is much higher than that of my thermistor. So the amount of current that I have in this circuit is defined by the value of these two resistances that are standard resistances, but they have a very high value, say rather something like a gigaohm. And therefore I inject this current, and therefore I am dissipating a power here. And this means that the temperature of this crystal will be a bit, when the thermistor is biased, is a bit higher than the temperature of my bath or my cryostat. And this is the relationship. This is the power that is dissipated, the conductance, the thermal conductance between the crystal and the bath, and the temperature of the bath. So the voltage across the thermistor provide a measurement of the temperature of my crystal. Okay, because the voltage depends on the resistance depends on the temperature, and the temperature of the crystal is different from the temperature of the bath. Now assume that I have a particle that is depositing an energy in the crystal, produces an increase in the temperature of the crystals, and therefore I see a change in the voltage across my thermistor. And the change in the voltage depends on the energy that I have deposited inside the crystal, times, here you can see the details, but times what I can call the thermal gain of my device. Therefore, these thermal gains measure my sensitivity in translating a temperature increase into a voltage change. And a point that is important to remind, to keep in mind, is that this thermal gain depends on the temperature of the crystal. On the temperature of the crystal, because it depends on the resistance of the thermistor and so on. So if I dissipate more power, or if I increase the temperature of the thermal bath, the thermal gain of this device is changed. And this is how the signal develops in time. You see, when I do not have signals, I have what I've called the bias of the thermistor. And since my electronics is DC coupled, I'm able to read out this bias. So in this portion of the waveform that usually I digitize. In this portion, I am able to see the voltage of the thermistor before the energy release. And therefore, I'm able to measure the temperature of my crystal before the production of the signal. And this is important because it means that I'm able to evaluate the gain, the thermal gain. Yes, we make average. I mean, average on the sampled points, on the sampled points. We can, I mean, we have different techniques. We have, at the end, we are not using for the analysis, really, this is filtered, and we use a technique that is called optimal filter. So, I mean, there is a bit of machinery, but in any case, I mean, the point is you use all these sampled points to evaluate the voltage. You have, we also fit in order to understand if there is a slope. Okay, but the important point is that I need to measure this gain. And then, of course, I will need an absolute energy calibration of this gain because I want to see possible changes in the gain, but then I need to convert this voltage into an energy. And this is done with standard calibration as you do for all the detectors. The only point is that we have to be careful of changes in this gain due to temperature changes. Then you have the development of your pulse, the pulse height that is evaluated with an optimization of the information that you have, and this is done with what is called the optimal filter. But in any case, this voltage change provides the measurement of the energy. And you also can evaluate the noise level, again, using these first samples. You can measure the noise level that you have when the signal is collected. So real bolometers look like this. These are arrays. And you can look here. You have the crystal. The crystal is mounted inside the copper holder. The reason why we choose copper is that it has a very good thermal conductance. So the copper holder becomes our heat sink, heat bath. And in order to, I mean, we have a mechanical problem. We need to hold the crystal inside this skeleton of copper, and a thermal problem. We need to avoid that a too high thermal conductance between the crystal and the holder reduces the amplitude of my crystal, of my signal. Because, I mean, if the amplitude of my signal is proportional to the energy that is deposited into the crystal, but you see that if I have a very high conductance, it's very difficult to and immediately you have a heat flow toward the bath, you reduce the pulse amplitude. And so you need to have some kind of equilibrium, and this is done by using, I mean, equilibrium optimization is using Teflon, PTFA, stands or supports as you like that hold the crystal in position and avoid to have a direct thermal contact between the copper and the crystal. And then here you can see our thermistors, and we also have a heater for technical measurements. Yeah. Yeah, so, okay. The model is quite complicated. If you want to describe the whole, either the rise time, the decay time, and all the parameters that describe this pulse depends on temperature. Okay, so maybe they change a lot, or they change. I mean, they have a dependence on temperature that is not easy to describe even. In a first approximation, we can think that in the development of this signal, the heat capacity and the thermal conductance are a number, but this is not true. Also, thermal conductances depend on temperature, especially not the thermal conductance of a material, but of the interface that is called the Kapitsa conductance. And that depends, if I remember well, with the temperature to the third. So is an important depend, or the second, I don't remember now. So they have a dependence. Yeah. I will show you a model, but I mean, it's complicated because you do not know exactly the value of these parameters, and that depends on temperature. And moreover, you don't know if, I mean, the model that I can model like this are reliable, because in principle you should describe your detector in terms of phonons that are transmitted to the sensor or to the heat buff. So it's not. Yes, okay. You need to find an equilibrium, okay, a compromise. So the copper here stands for this thermal buff. The copper has a very high thermal conductance, is in a very good thermal contact with the coldest part of your refrigerator. So you can think of copper as being the thermal buff. And Teflon is what I have here, is this thermal conductance. Indeed, I should represent this with a thermal conductance between the copper and the Teflon that has its own heat capacity, and then the thermal conductance between the Teflon and my crystal. And these two thermal conductances are contact conductances, and in order to, they have a dependence on temperature, and you also need to know, which is not easy to evaluate, the effective surface that is in contact in between the two materials. So the truth is that it's not easy to model. At least what we do is, once we have we are able to do measurement, we try to design a model and fit the model on the data, but we are not able to do the other way around. So right on our notebook, the heat capacity and the conductances that I expect to see in my detector, and then decide I want to have Teflon pieces with this dimension. I want to have this pressure between the Teflon and the crystal, and so on. This is at the end, this is based on the experience and on a lot of tests, but it's almost impossible to do it on your table and sit down and write. No, well, it's a good insulator. It then an additional point is you need to when you cool down materials, they change their dimensions. You have contractions, and different materials have to have different contraction. So you need to also to consider that. In that case, you can rely on tables that provide you database that provide you the information. So one point is that you need all the contractions of the different material to fit with each other. You need that material do not change behavior when it is cooled down at low temperature. Keep in mind, when you need to test all the properties of materials, you do not need to go to 10 millikelvin. It's enough to go to test them at nitrogen. Between the rule is between nitrogen or helium, between nitrogen and 10 millikelvin, nitrogen is 77 Kelvin, or if you prefer liquid helium at 4 Kelvin, that in any case is a temperature that is easy to achieve, to reach with a small cryostat and that you can have in your lab. And in between the, say, few Kelvin and 10 millikelvin, nothing relevant, at least from the point of view of mechanics, change. So you can really test that temperature. And then one more requirements that materials has to fulfill is the radioactivity. So Teflon is, if you select it, is very good also from the point of view of radioactivity. The same is true for copper. So at the end, when you have to design your detector, you discover that all these constraints reduce the number of materials that you can use to design your holder and so on to very few. So this, for example, is assuming that everything happens with thermal phonons. This is the model of a bolometric detector like the one that I've shown you. So this is the tellurium dioxide absorber. This is the part with Teflon that I've drawn here on the blackboard. And then also the thermistor is not as simple as you could guess. In the thermistor, we have, well, first of all, of course, we have the glue. And let's neglect the heat capacity of glue. And then we have thermistor. And the thermistor have wires. And wires are connected in some way also to the thermal bath, because they are metallic wires. And so at the end, they provide an additional conductance to the thermal bath. But the thermistor that we are using, in these thermistors, when they are operated at low temperature, there is the behavior of phonons and the electrons can be described as if there is a thermal conductance between the lattice, therefore the phonons, and the gas of electrons. This is a semiconductor, as I've told you, but it's doped at close to the transition between metal and insulator. And in that case, you have a kind of, I mean, the electrical conductance happens through a mechanism that is called variable range hopping. And I mean, you have electrons that can move as if they behave in some way as being a gas of electrons with their own heat capacity. So the structure, I mean, the model is this one. And so the optimization of all these conductances should aim at the present configuration, at the configuration that I designed with this, I've drawn with these arrows. When you have heat produced by a particle that is interacting in the crystal, you would like that most of the heat goes into the direction of the sensor. Of course, you will have a small amount of heat that will go in this direction through the Teflon. Then you will lose a fraction of the heat through the conductance of the lattice toward the heat buff through the wiring. And again, you would like this to be very small because you want to hit the electrons. Because here in the electrons, you have the production of your signal that is read out by the electronics. So coming back to the experiment, this is the history of our detectors. We started in the 90s with these few tens of grams crystal, and these are all the parts in which we cutted the 100 gram crystal that we were not able to cool down. And then we scaled it in mass. And meanwhile, the results of our experiment improved. And I remind you, when this is not the sensitivity, it's really the lower limit that we were able to set on the neutrinoless half-life. But I remind you that sensitivity and also this the result depends on the mass, the exposure, mass times the duration of the measurement, and the background. So you don't see in this plot, but we did increase the mass, but also reduce the background. And then we started building arrays of crystals like this, and now we are operating this big array. Here are more or less the numbers that are used for this plot, and so you can see also the background, and you see that this first experiment is the first array that you see here, and the background in the region of interest was 0.3, and then with Quarry we are at 0.001. So the strategies, I mean, the strategy for to increase the sensitivity is reduce background and increase the mass. Let me briefly describe you how we worked on background reduction. I also prepared 2 exercises for you on that. I will post on the folder of dedicated, so this afternoon you can look at them. So the first step is to identify the sources of the ground, and we already discussed a bit in the first lecture what are the sources of the ground, and then work on their reduction. This is not the first array, but Cuoricino was the second one. We have the second large array, because we also tested arrays of 4 crystals. And this is the result of Cuoricino. So look at the black histogram. That is the physics data. So how do we collect and how do we operate a detector? We do that like this. I mean, we build the detector, we cool it down, and the detector is an array of crystal. And each crystal has its own thermistor and its own readout chain, its own trigger, its own digitalizer, and then, okay? So it's really, each crystal is really completely independent from the other. So we collect data. From the pulses, we extract the information on the energy. And then we fill histograms. We will have one spectrum for each of the crystals that we have in the detector. And then we sum all the events in the same histogram. So here, the events that you see here are collected with, it's not written here, but they are 44 crystals. Okay. As I've told you, we need to calibrate our detector, and this is done periodically, say every month, every 15 days. It depends on different condition. And this is done, I mean, this is in your cryostat, and this is done with an external calibration source. In this case, the calibration source is thallium 208, is a standard calibration source. And in the red plot, you see also the calibration. And this calibration source, indeed, it is a thorium calibration, but there in that part, I mean, at this energy, the only contribution comes from this. The only contribution to this spectrum from the calibration source comes only from this isotope with a line, a gamma line, that has this energy. And this is one of the lines that we use to calibrate the spectrum. So you see that both in the data, that is the black spectrum, this is the spectrum that we use to decide if double beta decay, neutrinoless double beta decay exists. If it does exist, we should see a peak over here, okay? Either in the spectrum and in my calibration, I see this peak. And the reason why the two peaks have the same height is just that I have normalized the calibration to the physics data. Okay, so the rate is completely different when I'm calibrating. I just normalized. And what do you learn from this spectrum? Well, what from this comparison? What the first outcome? You look at this spectrum, and what do you learn concerning the background in the double beta decay region? Something that you can infer from this plot. Yeah, no, this is not completely. You cannot do that. Say that only with this plot, but more or less, yes. There is I mean, complementary information. If you have sources that behave, a thallium source that behaves as this calibration, I have a background coming from this line that populates also the double beta decay region. So this red spectrum, of course, depends, but not critically, on the position of this source. But believe me, even if I move this source over here, and even if I deploy the source inside the detector, I will see events over here. So for sure, in my data, a fraction of the events that populate the region of interest have to be correlated to this thallium line. Yeah. Oh, no, yes, but the peak, but this is what we do. But the peak that you see, the black peak, is not due to calibration. I mean, here you see the superposition of calibration, but if there is a peak here, also in the black spectrum, and that is the ground. So I have a background source that produces this same line that you see in the calibration. Okay, so if I just draw, I don't have a plot here, but if I simply draw my okay, this is the spectrum, my physics data spectrum, and this is the thallium line. Here, what I'm doing with the calibration, if you want, is to avoid using a Monte Carlo simulation, but use experimental data. And but I mean, is more reliable than the Monte Carlo calibration. This is the truth. If I put a source over here, I see that spectrum, and therefore, if in my data, physics data, I see this line, I have to take into consideration that events populating this region should be due to a background connected to that line. This is color that. Okay, the other two peaks. Well, the point is, generally, each peak produces a contribution. I mean, a peak is a monochromatic line and can produce, due to some kind of degradation of the total energy that is connected to that line, can produce only events below that line. Okay, so these peaks do not produce by themselves, they do not provide contribution in the double beta decay region. This peak is, you want to know the origin of this peak? That peak is due to cobalt 60, and it is due to a cascade. So cobalt 60 produced two lines, gamma lines, at 1173 and 133.32 kV. Okay, this is the source we discussed yesterday. And the level scheme is like this. So you have a beta decay on this level, and then you have the excitation, and following the excitation. I don't remember which is the order, but you have these two gammas. And they are correlated and in space. Therefore, when you have all the spin aligned, you have the emission in this case, we do not have spin aligned. This is the peak that is produced when I have these two. I mean, this are both of them are prompt line, so they are detected simultaneously in the same crystal, and so I see the total and the sum energy of the two. And I wanted, okay, this is mainly produced by cosmic ray activation in copper. That is why we have this special agreement with a copper vendor in Germany that is working for experiments that are operating in Gran Sasso since really a long, long time. They cast copper, store underground it, and then when they are ready, they deliver the copper to Gran Sasso in order to avoid cosmic ray activation and to reduce this to a minimum. It's not that much. As I told you, since, I mean, this peak does not provide contribution over here. Can you guess when cobalt-60 is a problem for this experiment? Sorry? When do you not have it? Oh, yes, of course, but assume that I mean, we stick on bolometers, so we have this energy solution, but resolution, but no. Yeah. So the problem is these are the two gammas, but then you have also the beta, the electron. So if the contaminant is in the copper, the electron stops immediately and its energy is fully absorbed in the copper. But if, for example, the cobalt is an isotope that contaminates my tellurium dioxide because it was produced by a spallation process on tellurium, then in that case, I also have the beta. And therefore, I add some energy there. And therefore, this can be, it could be a problem even when it is really on the surface of the copper, because in that case, it can happen that both the two electrons and the beta are emitted, but the efficiency in that case is very, very small. What? Okay, good question. So, of course, you can see both, not for, I mean, in principle, you can see spallation both spallation or cosmogenic activation both above ground or underground. Of course, the fluxes are much different. We do not see, and we are not worried of spallation processes when the tellurium is underground, because they are I mean, the rate is very, very really negligible. We have some hint of activations of other isotopes in Cuore due to the underground neutral flux, but not in the region of double beta decay. Well, yes, but it depends on the half-life. I mean, this has 5 years of life. That is rather nice because when you construct an experiment, it takes some time. So even for the tellurium dioxide crystal, we had the same policy of storing the crystals underground as soon as they were delivered from China. But we had, I mean, you have to be careful and understand if you can make, I mean, deliver the crystal by sea or by flight. Because at high level in the atmosphere, you have a higher neutron or proton flux, and therefore spallation processes are more important. But of course, if you deliver by flight in 12 hours, they arrive from China. In the other case, it took even 6 months by shipping. So you need to find the balance. But I'm not able to see 2 electrons. I see the sum of the energy and also for gammas. So I only count event in this, with this detector, I'm able just to count, to measure the energy that is released inside the crystal, but I have no idea of the particle that has released that energy. So, and even if I have a simultaneous energy deposition due to beta, gammas, or alphas, I just sum up everything and I see the energy. So, yeah. Well, in semiconductor technology, you are not able to distinguish a gamma from an electron because gammas and the electron have the same interaction because a gamma interacts on electron. Okay, the only point is what I've told you in the first lecture, maybe, is that a photon generally interacts in a different position inside your detector. And therefore, the signal formation, especially the charge collection, is sensitive to the position where the first ionization was produced. But this Riccardo Pruniera from Legend will explain you very well because is a technique that they use to distinguish Compton to distinguish the interaction of photons from that of electrons. But in principle, it's not really the fact that your detector has a different sensitivity to the way the particle is interacting, because they interact always on electron. It's just a position dependence. And in this case, we do not have position dependence. Okay, so the other point, so no, let me come back. So you see, from this comparison, what I learn is that since I see this thallium peak in my black spectrum, that is my physics spectrum, I should expect that also there are events that populates connected to the related to this thallium peak that populate this energy region, because this is exactly what I see in the calibration. I can do the same with a Monte Carlo simulation. Okay, I can run a Monte Carlo simulation simulating what what the detector should see when I have a contaminant here or on this shield or in the different position. But as I always try to convince students that Monte Carlo simulations are very helpful, but only when before running them, you already know the result, more or less. Otherwise, since it's very easy to make some mistake in the modelization or in the use of the code, you can draw conclusions that have no meaning. So it's always important to have an expectation and to have some data that you can use for comparison. And a calibration is very useful from this point of view. Of course, you have to be careful, and this you can guess from what from your knowledge concerning the interaction of photons with matter, that of course this shape will depend on the position of the source. And then, and then of course, what you can guess from this comparison is that very likely there is some additional contribution, okay, that is not in relation with this thallium line. And this you can guess both from the fact that this, you see this shape, okay, so it doesn't fully explain. The peak is normalized, so they have this, they are the same height, but the background is completely different. You can guess from here. And also you can guess from the fact that here you see this flat background, and there is no mechanism that you can imagine that should make this background immediately drop exactly where there is this thallium line. So you should assume that this background in some way, maybe not exactly, could change a bit its shape, going down to lower energy, but should extend also over there. It's quite reasonable. So if I show you the spectrum on a wider range, you can see that there are a lot of peaks in the energy region that is generally called the alpha region, because it's populated by alpha lines. And this was for us an important milestone to understand that this flat background is due to alphas as it is for these lines. So again, two of the exercises that that I suggest to you for this afternoon are connected to this spectrum, so I do not. I will go briefly on this. You see, these peaks are wider than the gamma peaks, and there are two reasons. One is connected to the specific distribution of the contaminants, and the other is due to the fact that in this region I don't have I have to extrapolate the calibration, because gamma calibration stops here, and this is you see my gamma calibration. So I don't have lines here, and so I have to extrapolate. And whenever you have to extrapolate, you have in extrapolation the uncertainties increase. And the problem is that here I sum over 44 crystals. So I have fluctuations in the of one crystal toward the others in the position of the extrapolated position of in energy. And so this produce yes, artificial enlargement of the peaks. And the same happens also for the same crystal, because I collect data in different runs. Each run that lasts, for example, 15 days has its own calibration. And then I have to sum spectra, calibrated spectra, and again, I have the same problem of extrapolation. So in any case, for what I want to discuss this morning, the message is we discovered that the second important contribution to background in the region of interest was coming from this flat background that is due to surface contamination of the materials surrounding my crystals. And this I was able to describe also with a Monte Carlo simulation. So you see, we have 3 different contributions that are reported here in this spectrum and compared with the data. Again, the data are the black histogram. The green, no, let me start with the red. The red histogram is what Monte Carlo predicts for events produced by crystal surface contaminations. The green one you see is the green spectrum. You see is the one that explains this flat background, is a Monte Carlo prediction for copper surface contamination. And when I say surface contamination, they are in uranium or thorium chains. Each of these chains produce about 5 alpha particles. And then the other is a cryostat contamination in thorium-232 that is the chain that to which the thallium isotope belongs. Okay? So I identified my dominant background contribution. First, this the most important is this copper surface contamination. The second one is the cryostat contamination, and the third one is crystal surface contamination. This so these events in the flat background, in the flat region, are due to this process. So keep in mind, let me go back one step. Something I forgot to tell you. My crystals are held in vacuum. Okay, so I have a Teflon stand here, and then copper. For example, this is copper here. And then vacuum, no air. So the energy, whatever the contamination and its location, the edge energy can be degraded only when my particle is emitted and is crossing one of these materials. And my detector is sensitive in the whole volume, does not have a dead layer as it happens, for example, for most semiconductor detectors. Okay, this is an important point because it's really critical, and in most other detectors you do not have this problem. In semiconductor detector, there is in germanium diodes there is a very small surface area where the detector is sensitive to surface contamination. You will see, and they see a bit of some alpha emission, some alpha activity. And but in our case, it's the whole surface of the crystal. So when you have a decay somewhere, assume you have a decay in here, and you have a recoil and the alpha emission. You have the recoil is fully contained. A fraction of the alpha energy is released inside the crystal, but a fraction goes out. So this decay is produces a monochromatic alpha and a monochromatic recoil, but you lose some of the energy outside the crystal. The same happens when you have a decay over here. You can have the alpha that is emitted in this direction, the recoil in this one, and the alpha has 5 MeV energy, but 2 MeV are deposited inside the copper, and only 3 MeV are deposited inside the crystal, and so you have an event in that position, in that region. While for surface contamination of the crystals, well, there are also coincidences. Again, there is an exercise this afternoon. We will go back to this discussion in the afternoon. Oh, this one. No, it's a problem that you will have to face. This is okay. So this is platinum, and platinum is platinum 119, and is a contaminant that is introduced through the crucible that is used to grow the crystals. So in as natural contamination, and the problem, additional problem. The problem is that probably it is introduced not exactly as a single nucleus that contaminates the crystal, but as a spot of platinum with its own heat capacity. And therefore, the signals due to this, if you look at signals that produce this peak, you discover that they have a different shape. But they are not that some different enough to be rejected by our pulse shape analysis. No, we don't know. The shape, the reason of the shape is due to the fact that yes, that according we have crystal. I mean, in Quarry it's not as high as here, but we have crystals that have a high contamination and crystals that have much less contamination. And we know also that it comes from the crucible because we've isotopically enriched crystals that were in Cuoricino, but they are not in this plot. We had to regrow several times the crystals, and so we accumulated these contaminants, and we have a very high peak. But yes, that is. We made some study to understand if this peak has a tail toward the low energy region that can produce this, but it doesn't likely. Okay, this is the answer to your question. And then the third step, once we have identified the second step is to, I think I made some mistake. And there's something missing here. In any case, the second step was not to describe the platinum peak, was to reduce contaminants. And so what we have done is to change the polishing treatment of the crystals using radio pure components. The same for the copper. And for the thorium contamination, This is a contamination that likely is due to a material that is always used in cryostat that is called the superinsulation. You have either to change the cryostat, removing the superinsulation, especially in an old cryostat, is not easy, or to add an internal shield surrounding your detector. And then we also developed a tool for Monte Carlo reconstruction. Is a tool based on Bayesian analysis that combines all the Monte Carlo that we run for all the possible sources placed in all the possible positions. And the free parameters are the intensity of these sources, and you reconstruct the background. We have more than this observable. We have also information on coincidences, and then we reconstruct the background. And once you have reconstructed the background, you can define a strategy to reduce the most important contamination. So, strategy for mass increase. Well, you already have seen this. The strategy is that we put in place over the years in this plot. At the beginning, we increased the size of the crystal. There is some limitation in the size of the crystal. Of course, it is easier to operate a big crystal than many small crystals. You have only one big crystal to analyze, to calibrate, to mount, and so on. But there are limitations in growing big size crystals. And so then we started increasing the number of crystals, building array of detectors. And with Cuoricino, that is this array, and Cuore Zero, that is as an array of the same size, we have used the same cryostat, that is a customized commercial refrigerator produced by Oxford Instruments. But when we decided to jump to a much bigger detector, we had to face the problem that no big cryostat did exist at that time. The idea, the size of the commercial cryostat at the end of the 90s, Core Idea was born in 1997, was this one. Okay? And so we had to decide what to do. And the decision was to build a completely custom cryostat. So let me come to Cuore. This is the Cuore array. So a few words on the cryostat. At that time, only two big cryostats operating ton scale gravitational antennas did exist. The first was a customized Oxford Instrument cryostat, but reached 100 millikelvin, but the antenna was not operated at that low temperature due to problem, and it was operated at a few Kelvin. The same happened for a smaller cryostat and a smaller antenna, that is this one, that reached a bit lower temperature, and again, it was operated mainly at much higher temperature. And this cryostat was designed by Frossati. He was first in Oxford, so almost all the low temperature refrigerators are operated thanks to something that he's designed. And it looks what he's designed is a heat exchanger. And this is the critical point of cryostat. And so we contacted him for the design of the dilution unit of Cuore. So this is the Cuore cryostat. This is the dilution unit designed by Giorgio Fossati. And here is installed in a test cryostat. This is the Cuore cryostat, and I already shown you the full cryostat with a rendering of the Cuore array. It was really challenging. So when we cooled the cryostat the first time, we really did not, I mean, we had a lot of doubt, okay? And it was really challenging, and it required more than about 1 year to be able to work with this cryostat. Now the cryostat is working with a stable temperature. Here you see the temperature, the fluctuation of the temperature, the base temperature of the Cuore cryostat, and you see they are at 0.1% level over several years. And now it's already running, so. We have also observed huge instabilities. You see them here. Can you guess what produced these huge instabilities? You see, this is quite huge, 100 millikelvin. The other are not so big. Vibration. This was a blackout. This was an earthquake in Albania. And this was maintenance, and this was the insertion inside the cryostat of the deployment of the calibration sources inside the cryostat. We used them once. We discovered that the cryostat was not stable, and so we decided to use external calibration. But I show you this because, I mean, earthquakes are a problem. We have to reject data during earthquakes often. And we see earthquakes also in Australia or in Japan and so on. And we also discovered that there is a clear correlation between the noise that we see in our detectors and the sea waves in the Mediterranean Sea. And since sea waves have a seasonal variation in their intensity, we see a seasonal variation in our noise and in the resolution of the detectors. So a few curiosities on the detector construction. How challenging can it be? Okay, purchase the crystal is the easiest part. We just have to decide if we want them to fly or not. We have to glue thermistors on top of them. We have to design and produce the mechanical parts of the holder. We have, as I was mentioning before, constraints on the material that can be used both from the point of view of thermal properties and of contamination. The holder is made of copper. We had this special agreement with a germanium vendor, but we also need a special copper from the thermal point of view. And we need that this copper does not contain hydrogen. Otherwise, the spontaneous conversion of orthohydrogen to parahydrogen release heat and implies that it takes a lot of time to cool down the cryostat. So the reason why we use an internal lead shield and not copper, because copper is a very good shield, and copper often is more radiopure than lead. The reason is that even if copper with a low content of hydrogen does exist. We were and we are still worried by adding too much copper inside the refrigerator. And so the mass that is needed to shield the detector is very high, and we decided to rely on LED. As I've told you, we have to clean all the parts, but we have also to handle and machine with a special prescription and so on and so forth. And here you see how the assembly line of Cuore worked. We had first gluing, then the assembly of the tower, and during the assembly, the tower grows in height. We have the bonding, and then we have stored each tower under nitrogen in order to prevent from radon contamination. This is the result, the result of several years of work with Cuore. You see 3 histograms, and the first one, the histograms are obtained summing over all the detectors and over all the runs. The double beta decay region is this one. You see that the shape of the histogram is more or less the same as the one that I've shown you for Cuoricino. The 2 color, I mean, the histogram of 2 colors refer to different cuts, selection, data selection. So we have base cuts that remove events like noisy events like those in which we have, I don't know, earthquake and so on. Then we operate the detector, all the detector in anti-coincidence. That means we accept only events that produce a single signal in one detector, and all the other crystals are not firing. This is very effective in removing the background. And then we add also pulse shape analysis to remove deformed signals. And then for each cut, we have to evaluate the efficiency. Therefore, the amount of double beta decay signal that we may lose applying that cut. They are the same 2 that we were seeing. Yeah. So I told you the identity of only on one. The other is due to bismuth 214 is the in the uranium chain. The energy of the line is 2448 keV. Yes, are due to contaminants in the structure of the crust. Okay, this is the half-life limit. You see in the region of interest, we fit the peak and the 60 cobalt peak, which is very close to our to the transition, double beta decay transition energy. And okay, next, what is the next step for us? So now we are very close to the final goal of Cuore, because now I've shown you that the sensitivity, Cuore, as you see, is an experiment where we work in not in the 0 background condition. We have background. The sensitivity increases at the beginning in a linear way, then with the square root of the exposure. We are now in this region, and as in a lot of experiments from double beta decay to gravitational waves, there is once you have achieved a reasonable sensitivity, there is more gain in stopping, upgrading, and restart the measurement than keeping the collecting statistic. And we are very close to this with Quarry. So what could be the next step? The idea for the next step is this is the same plot I've already shown you. The next step is to be able to fully explore the inverted hierarchy region. This is the same goal of the other big experiments proposed in the world. So, I mean, at the end is you have to be competitive with the other experiment. So the goal is very clear. And our strategy is to avoid to change the infrastructure, but simply to replace the detector. And how can we increase the sensitivity replacing the detector? Replacing the detector means that the mass, we do not scale on mass. Therefore, we have to scale only on background. Okay? And so how can we do that? This is the background model of Quarry. So is the reconstruction of the background. The background, sorry, is the physical data. We call it generally background because all the events that are there are background. And if we don't see neutrinos double beta decay, they are only background. So we made this fit that I discussed a few slides before. We simulated the effect of contaminants in different with different geometry in our setup. We fitted the simulation on all the data we have, and so we were able to evaluate the intensity and the position of each contaminant. And so this is the reconstruction. We have grouped the sources into 3 different components, and they sum to the data. So one is the gamma background component. So here we do not, I mean, we have used Monte Carlo simulation. And in the simulation, we also record, in each simulation, we record the identity of the particle that is depositing energy inside the crystal. In this way, we are able to sum, I mean, to group the result of simulation, not according to the position of the source, but according to the particle that has deposited the energy. And so we discovered that there is a gamma beta component that is this one, orange, more or less. It produces this spectrum. And this is the region of interest of Quarry. And you see that this spectrum has really a step here, and above the thallium line, this is the thallium line, the beta gamma background is very, very low. In this, there you have betas that are coming from thallium and bismuth 214, but they are and few gammas from the same only from bismuth, but with very, very low branching ratios. So the strategy was for us to change the isotope and move to an isotope that has a higher transition energy. In that case, with the same infrastructure and the same contaminants, we gain more than a factor 10 in background from the point of view of beta gamma background. Then we have an important source of background that in any case is there also in that region. It's the green one that is due to the alpha component. And there the strategy is to be able to identify alpha particle and reject them. And finally, you see the other component is the muon component. And this is there because in Quarry we did not build a muon veto because it was not needed. You see that is more than one order. The contribution of this component is more than one order of magnitude lower than the background we measure in Quarry. And so simply we will build construct a muon veto surrounding our detector. So the main point is, okay, I have to choose an isotope with a transition energy in this region, but we have already seen that they do exist. But also I have to be able to get rid of alpha particles. And this can be done using what we call a double readout technology. So what I do is to use a scintillator as absorber, so that, and then a light detector to detect the scintillation light. So my absorber is the double beta decay source, okay? So replaces the tellurium dioxide crystal. Tellurium dioxide crystal do not produce light. The only light that produces Cherenkov light is a development, I mean, is an R&D that we are doing, but for the far future. There are other double beta decay candidates that can be embedded in a crystal with scintillation properties. And so this big crystal is the source and also the device that we use to measure energy. Because the fraction of energy that you lose through scintillation is very small. So we can assume that the heat signal recorded by the absorber is a good measurement of, provides a good measurement of the energy released by the particle. We read out the light, and what we know, because this is the way a scintillator works, we know that the light produced by scintillator is different, both in amount of light and also in the shape of the signal, according to the particle that is interacting. Generally, for the same energy deposition, the amount of light that is released, in the case the energy deposition is due to an alpha particle, is much lower than the one that for the same energy deposition is produced in the case of a beta or a gamma. So when I draw a plot when for each signal, I report the heat, the amount of heat that is characterize this signal and the amount of light, I see two bands. This one is characterized by higher light signal, is populated by beta gamma events, and the neutrinoless double beta decay signal should stay there. The other is due to alpha events. And so the crystal that we have selected is LMAO, is lithium molybdate. It's a very bad scintillator. At room temperature, you are not able to see any light. But at 10 millikelvin, you see the same plot that I've shown you before looks like this. And these are alpha particles. And the blue dots are events due to beta gammas. So with this device, I'm really able to reject 99% of the alphas. 1 minute to tell you the final point, and then in the afternoon, if you want, if you have curiosity, we can go ahead. How can I read out the light? Because I've told you most of the devices, semiconductor devices, does not work at 10 millikelvin. So, and also pulse tube cannot work. And so I use a bolometer also to read out the light. So I use a wafer of germanium with a neutron, a thermistor, exactly as it is for this, for the absorber. The signal has a much lower energy, but the heat capacity of this wafer is very, very small, and therefore I'm able to see them. And there is an additional problem. Whenever you operate a scintillator, you put it in connection, and we call it the optical coupling, with your light detection system. And this is because you want to extract the photons and avoid the internal reflection of them. But we can't do that, because otherwise we add a thermal conductance between this wafer and our crystal. And this spoils the behavior of the crystal. So we have a vacuum in between the crystal and the light detector. And this is a big problem, because the efficiency with which the photons can go out from the crystal and enter the light detector is much lower, because the refractive index of the crystal and that of germanium is high, and the refractive index of vacuum is 1. And that's it. Yes, the drawing was different. Yes, you cannot see the slope here because you are dominated by the energy resolution. I mean, this spread is due to the energy resolution of this device. So you are not sensitive to and moreover, no, this is really the light yield. I mean, you have some slope, but you cannot see it very, very well. And then keep in mind, this is not an absolute calibration of the light yield. This is just the amplitude of the signal that we record. So this is an ideal this is really the light signal and the heat signal. In this plot, what you see is the height of the light signal that you record over here, and the height of the light signal of the heat signal that you see over here. This one is calibrated, this one not very well calibrated. For better detectors, better scintillators, it's you can appreciate the trend. But here you're dominated by other effects. So at the end, you simply rely on the distribution. And moreover, often we do not use directly the light yield, therefore but often we just use a pulse shape parameter in the light, because also the shape of the light signal is a bit different. And then keep in mind that the amount of energy, the amount of energy in this case of the light yield is very, very small for this detector, okay? So you are nearly close to the origin, because the amount of the scintillation is very, very, very small. In other crystal, you see it better. And when scintillation is important, also monochromatic lines in this spectrum appears with a slope, because you have a sharing of the energy. Here you cannot see the sharing of the energy because I mean, the amount of energy that is lost in light is so small that you cannot see that. Yeah. Yeah. And we also, I mean, in other crystals that we decided not to use, but that we tested, we also, in order to improve the energy resolution on the heat channel, we rotated the spectrum combining with light, and this provided a small improvement in the energy resolution. But in that case, in this case, the light is too low to have any kind of gain. Unfortunately, because we would like to have. Yeah. That's good enough. Definitely good enough. And we need also to use the light detector for a different study. It's something that we discussed yesterday because somebody asked me, maybe Giuseppe, that is the rejection of pile-up events. And in that case, we need to use the light detector because and not the heat signal, the light signal and not the heat signal, because light signal is much faster. But the signal to noise ratio, as you see in this plot, is very bad. And therefore, we are working on a new device where we add also an electrode on the light detector to drift carriers when you have ionization after the deposition interaction of the photon, to drift carriers in order to amplify the signal and improve the signal to noise ratio in order to be able to reject the 2 neutrino background that we discussed yesterday. And that's something we discussed. Okay, so we have lunch. Then I have a few exercises that we can do in the afternoon. And then if you have curiosity and so on,